Hello, calculus fans. Let's try another optimization problem. Okay, so you're playing fetch with your dog on the beach, and you're standing on the shore of the water, and you throw the ball 5 meters, and where it lands in the water is 3 meters away from the shore. Okay, so here's the picture. All right, so it's a little bit of a crude picture. Maybe I should have water out here. This is the water, and then the beach is on this side here. Okay, so water above that horizontal line, beach to the left, underneath that. We're starting at point A, that's where we're standing, and we're throwing the ball 5 meters towards point C. So the ball lands at point C. Now the dog is going to run along the beach from point A to point B, and then he jumps in the water and swims a straight line to point C. So your dog swims at the rate of 0.5 meters per second and runs 3 meters per second. And so let's say it takes the dog 7.25 seconds to get to the ball. Could your dog have gotten there any faster? So this is an optimization problem. We're trying to figure out, can the dog do any better basically by choosing this point B? Is there a different point that the dog could run to and then hop into the water? Alright, so we're going to put a few extra things into the picture. So first, I just want to mark the point D. The point D is directly below C in the diagram, so that there's a right angle there. Now the other key thing is that we're going to define X to be the distance between A and B. Now X is the distance that the dog is going to be running along the beach from point A to point B. We're going to try to figure out what is the best value of X to minimize the amount of time that it takes for the dog to go from point A to point B and then to point C. So we ought to be able to see that the distance from A to D is 4, and that's just using the Pythagorean theorem. Okay, so as we've said, we're marking an unknown quantity to be X. That's the distance from A to B. That's the thing that we have the freedom to move around. So perhaps the point B that we should choose, maybe it needs to be closer to A. Maybe the dog shouldn't run so far along the beach before hopping into the water. If the dog delays the point, then is covering more total distance. Of course, we have to keep in mind that the dog swims much slower than he runs. So let's now write down an expression for the total amount of time that the dog takes to reach the ball as a function of X. Now that value of X is allowed to be between 0 and 4. You should be able to see that from the geometry of the picture. X can be, the point B can be anywhere between A and D, so the value of X can be anywhere from 0 to 4. So we'll use the formula, time equals distance divided by speed, and we'll use that to figure out how long it takes the dog to get to his goal. We'll end up writing down an expression for the total time it takes the dog to go from point A to B and then to C. Alright, it may be useful if you have the diagram handy, because we're going to move on now. So the distance from B to C is the square root of 3 squared plus 4 minus x quantity squared. So 4 minus x is the distance from B to D. So you should refer to the picture. That distance that we're calculating here, this is just based off the Pythagorean theorem. Now we know the distance from A to B, that's x. We now know the distance from B to C, it's this square root expression. So, and since we know the speeds involved, we can write down an expression for the total time. So the total time that the dog is going to take to get from point A to point C is x over 3. So we're dividing by the dog's speed, which was 3 meters per second. And then the time it takes to swim will be the distance from B to C divided by the swimming speed, which was 0.5. Now let's clean this up. We've got x over 3 plus 2 times the square root of x squared minus 8x plus 25. So all we did here was multiply out this expression and clean it up. Okay, so we're looking for the absolute minimum of this function on the interval from 0 to 4. We're looking for an absolute minimum because we're trying to minimize the amount of time it takes. So let's take a derivative and set it equal to 0. So if we take a derivative of this function, we should get 1/3 plus 2x minus 8 all over square root of x squared minus 8x plus 25. You should probably double check to make sure that agrees with what you get. All right, it's going to be useful to make a common denominator, so I went ahead and did that here. And since we're setting this equal to 0 because we want to find critical numbers, we can just go ahead and set the numerator equal to 0. So if we do that, we get this here. Now let's move things around, which we're going to try to solve for x. So the way we should do that is by isolating this square root expression so that we can square both sides and get rid of that thing. So I'll move the square root expression to the other side, and now we're going to square both sides so that we can get rid of the square root. Okay, so we square both sides, and now let's multiply things out. On the right-hand side, the square gets rid of the square root. The square also gets rid of the minus sign. Now if you multiply out that left-hand side, you end up with 36x squared minus 288x plus 576. All right, you have to go work that out, make sure you get that. And on the right-hand side, since we're canceling out the square root, we just end up with x squared minus 8x plus 25. Okay, what happened to the minus sign? It got squared also, so it's disappeared. Okay, let's move everything to one side. And we get this equation. Now, that is a pretty horrible looking equation, but keep in mind it's just a quadratic equation. And so, I don't know, maybe you can factor it, maybe you can't, but who cares? Let's just use the quadratic formula. So if we stuff everything into the quadratic formula, we get this, which admittedly is pretty horrible looking, but let's just go for some decimal approximations. So if you put all that into your calculator, you're going to end up with two values. We'll end up with about 3.5 and 4.5. Now, don't take my word for it. Go ahead and plug everything in. Make sure that that comes out to 3.5 and 4.5. Now notice that 4.5 is outside of the domain. There's really no point at all that the dog would want to run more than 4 meters down the beach. Why would you want to overshoot that point and then turn back and start swimming? So really, the only critical point we have is at 3.5. Okay, so let's use the closed interval method and plug both endpoints and the critical number into the original function, which was x over 3 plus 2 times the square root of x squared minus 8x plus 25. So we're plugging in 0, we're going to plug in 3.5, and we're going to plug in 4. All right, so I went ahead and did all that, and I got the three values, and I want to pick out the smallest one. So that's the smallest amount of time that it takes the dog to get from point A to point C. So the absolute minimum time for the dog to reach his goal is 7.25 seconds, and it occurs at 3.5 meters. So their conclusion is that the dog should run 3.5 meters down the beach before starting his swim. So he really can't do any better than 7.25 seconds. Okay, that's all for now.